topic here, which is physical time. And I'd just like to point out that he also has 2 books back here. One just came out this year, and I just bought one. So anyway, looking forward to hearing more from Pharis on physical time.
Good afternoon. Maybe I can speed it up a little bit.
We got to get this.
Go get that. Okay. Physical time is a question that's been bandied about a bunch of the emails in the NPA lately, and that got me to looking at it a little bit closer. So a lot of questions come up about time, and the first one that pops in everyone's mind is, does time run forward or backward? The only reason you asked that question, or only reason that question arose, was because of Newton's laws. Because in Newton's laws, there are other equations of motion. You put a minus sign in there and the equations still spit out the answer. There's one set of laws that you can look to that may give the answer, and that's the thermodynamic laws. And of course, everyone knows about the bull in the china closet shop and all that sort of stuff. So you have a sense that in thermodynamics things tend to go one way. Okay? So in writing the first law of thermodynamics, you find that there is an exchange energy that's equal to a change in the system energy, and then there's a whole bunch of work terms. At the moment, it's immaterial that I've got 4 work terms. Don't worry about that. But the big point there is that in the first law of thermodynamics, there is no time. Okay? Then the second law, well, in the denial of perpetual motion, we find that time can enter into the picture. And so if you work through the implications of putting those 2 laws together, here's a partial list of what you come up with. The first one is that there is an integrating denominator guaranteed for the path-dependent first law. That integrating denominator leads you to an absolute velocity that exists when that integrating denominator vanishes. That's an absolute unique velocity. Also, the first and second laws provide for the existence of a mechanical entropy. That is, that's a path-independent function that you can get from the path-dependent first law by dividing by the integrating denominator. The other one that is more pertinent to today's discussion is that mechanical entropy is an indicator of the flow of the dynamics in the first law. Okay, I simplified that first law where we only got one force. Okay? Notice I've allowed that force to be a function both of position and velocity. That's because this is a path-dependent equation. This change in the system energy is path-independent, so the force has to be a path-dependent. And if I only specified that the force is a function of position only, it would not be path dependent. I said the second law provides for a new function called entropy, which is path independent, and here is that integrating denominator. You notice the integrating denominator is only a function of velocity. Also notice that by talking about velocity, we've kind of introduced time in the back door. We haven't said what it is yet, but it has to be in our minds when we're talking about velocities. Okay, so we can, with the integrating denominator being a function of velocity and this new mechanical entropy differential has to be a path-independent thing, the only way that the force can be here is that in the force has to be a function of velocity. Namely, that function of velocity has to be the integrating denominator, because when we divide by it, we end up with a force that's only a function of velocity, position itself. What you end up with then is a integrable system. That is, it would be if we knew what this function of velocity for the system energy was, and if we knew what this integrating denominator was in terms of velocity. But what we see is it's separated out into some function of velocity and some function of position. Okay, so if we concentrate only on that kinetic part of the entropy, we have a differential equation that says the change in kinetic entropy is equal to the change in the system energy divided by this integrating factor. So we have a differential equation that we can seek a solution for, but we have the limiting values. That is that this integrating denominator has to vanish when the velocity approaches that absolute velocity. Okay? If that's the case, then these are the only functions that you can have for the system energy and the integrating denominator, and also for the kinetic entropy. That is, the system energy must be the mass times the absolute velocity squared divided by the integrating denominator. The kinetic entropy is 1/2 mass times that integrating absolute velocity by the square of that integrating denominator. And here is that integrating denominator where m is a constant in all this stuff. That integrating denominator looks for the world like that beta function that everybody talks about in relativity. I want to point out, though, that this is not that case here. Okay? The velocity that we used that comes up in this integrating denominator is the force-driven velocity that you get when there's a force in the first law. Okay, so this first and second law, to get, if they hold as a universal law, then they must hold for all observers, no matter what velocity they're going. And that all observers must see the same absolute velocity. That is this one. Okay. I've tried to get away from special relativity or relativity principle, so I've coined the thermodynamic relativity principle to try to remind people that if you're requiring two observers to see the same physics, okay? We've heard earlier today, perhaps tomorrow or yesterday, that there was no physics. They were talking about sending light back and forth, but they couldn't see any physics. Here, what I'm requiring is that all see the same physics. One situation that might occur that I've used as an example, and we're out west, so we got a cowboy around a campfire, and he's doing some physics. He's got a force, and he's seeing what it accelerates something. Well, you got his buddy going by on the stagecoach, and he's watching him. If this thermodynamic relativity principle is to hold, then both of the stationary cowboy and the guy on the stagecoach needs to watch that same physics and see that same limiting velocity, that same absolute velocity. So what does that do to us? Well, if our buddy on the stagecoach is flying by at some velocity w, and there's no requirement for this to be constant velocity, because tired horses can't run as fast as fresh horses, they go up and down hills. All you need to do is know the stagecoach velocity. And you then see, here's the force-driven velocity in the x direction. And so you work through that transformation and require that both the cowboy that's sitting by the campfire and the stagecoach guy have the same absolute velocity. And you find that you end up with this transformation. Now, cogitate on that transformation for just a moment. Where's the force-driven velocity? There's one in the numerator, and it shows up again in the denominator. When have you heard relativists, or those who argue against relativists, use the force-driven velocity? They always discuss kinematics. Okay? Kinematics in this case is the stagecoach velocity. And where does that show up? Down here in the denominator. So if you're watching no physics at all, then the force-driven velocity is 0, and this reduces down to the same thing they argue about as Lorentz transformation. Okay? Okie doke. So there are two velocities in this transformation, and there's no requirement for inertial frames. I haven't said a word about light, but let me say a little bit about light right now. How is the cowboy sitting by the fire obtaining his information about the velocity he's watching? And how is the guy on the stagecoach obtaining his information since he's flying by? Well, he can do it perhaps in 3 different ways. One, they can both get the information instantaneously, so there's no delay in the transformation of information from one to the other. And if that's the case, then this is what you see. However, if the thing they're watching is emitting light, then they receive their information by recording that light. Then there's a delay in the transmission from the object to both observers, and you must account for that transmission delay. If you're shining something on that object, then there's a 2-time delay. And now you got to talk about like that radar ranging we heard about this morning. But this is instantaneous information collection. Okay. All right. It's not the same that we see in the relativistic, but all must see the same absolute velocity. Okay, now let's turn to equations of motion, because this is where we physicists spend a lot of our time trying to figure out how things move. Okay? Our differential in entropy is the first law divided by the integrating denominator, like this. And so I can rewrite that now with, here is, I put this in brackets, and I've introduced time. Okay? This is the first time I've introduced time, and we see the old force and mass and acceleration product. But there is this crazy velocity function down here that shows in there too. But notice, this is just the result of the integrating denominator. In other words, this is just the result for the cowboy by the campfire, not for the guy on the stagecoach. But mechanical entropy, we found out, was a function of velocity plus a function of position, and then you can always have an integrating factor constant, and so the mechanical entropy looks like this. Okay. There's another way we can do equations of motion also, and notice that if we're playing the thermodynamic game, an isolated system has to seek a maximum of entropy. And I showed yesterday that the stability conditions give you a natural geometry for this, and that natural geometry shows up in here. That's not the important aspect. The important aspect, though, is that I can do that, and I end up with equations of motion the same way we had before, except that the kinetic entropy term is used instead of the kinetic energy terms of Einstein's special relativity or Newtonian mechanics. Okay? So we can verify these equations of motion by putting them in the first law. Okay? The first law is this, and so here they are. But what if our system is isolated? That is, there's no exchange of energy between the system and its surroundings, and that's what we need to make sure that the increase in entropy is required, then something has to be zero in here. If the velocity is zero, we've severely restricted ourselves. If dt is zero, we're looking at no physics in time. So that means that in order to isolate the system, this has to be zero. So what we end up then is that the change in entropy with respect to a change in time, and notice I divided it on both sides, and I used a positive interval of time, so I don't change my greater than or equal sign. And now I notice that entropy has to increase. Positive time, there's no way that an isolated system can go backwards in time. Because if I use the negative dt, get back here. If I use the negative dt, I'd have to reverse this to a less than or equal sign. That would say that the entropy was negative. Okay. Anyway, so the other thing I'd like to point out, though, is that get back to the physical time. If I scale the entropy with this constant, then I can talk about a physical time based on entropy, and it's proportional to this time only if this factor here is unity. Okay. If there is no force at play, this is zero. Okay. So what this points out is that the physics that's going on is the only thing that can change the physical time from the local time. Okay. Okay, so the conclusions here is if you start with thermodynamics and use the denial of perpetual motion, you end up with an integrated denominator that looks like this, a velocity-dependent force. We had discussions about mass effect, that is, things getting heavier so you can't push it. This argues that the force gets weaker. So in an accelerator, the reason that you can't accelerate it faster than some velocity is that the force goes to zero when you get to that velocity. And physical time is related to local time by the exchange of energy. Therefore, it also gives you an arrow of time.
Wow. That's great.
You know, there's every time I come to these conferences, there's like 2 or 3 that sort of really stand out as like, this is really important. And what you just did is one of those, at least for me, I seriously, because what I think you just did was you took electrodynamics and you were able to introduce an arrow of time by introducing a function which is a function of velocity into the equations, and so it no longer has this Feynman's problem of time invariance.
But you said I took electrodynamics.
Yeah.
There's none here.
Okay. But you started with equations that come from that.
Thermodynamics.
Yeah, but no, okay.
Okay. Now, yesterday I did show how thermodynamics led to electrodynamics.
Mm-hmm.
Okay. And also you can show that this absolute velocity we're talking about here, it becomes the speed of light when you get to electromagnetism, but you don't need that to show the arrow of time and the fact that the physical time is tied to this mechanical entropy.
The second thing that I thought, by introducing this idea of a function of velocity, I mean, temperature itself is nothing more than just something which is a function of velocity. So that phi function acts a lot like temperature. I mean, I don't know what you thought of that, but...
Well, I wasn't the first one that thought of that. In fact, Tom Phelps Sr. wrote an article. He published just a little bit before I did this in graduate school, and he showed that this was an integrating factor for the first law of thermodynamics. Yes, sir.
Hello. In special relativity and electrodynamics, there is a vector direction that's involved in these equations. for instance, on the force equation you mentioned for accelerators, there's an angle in there it's v squared sine squared theta over c squared. And I notice you don't have any angular dependence. Does that mean the thermodynamic approach is kind of averaged over all angles and not angle dependent like
No.
most of our experiments?
Not at all. That means I used only one force to make it simple. I didn't use a two-dimensional force in this example.
So if you use two-dimensional, you would have had angular
You
dependence.
use a 3, or if you use 4, you'll get angles. Yeah.
Okay.
Yeah.
This Prigozhin's approach about error of time. Prigozhin's, you know Prigozhin's work
I'm not
about error of time. Prigozhin's,
Okay.
Prigozhin. Do you know Ilya Prigozhin? Do you know this work?
No, I don't.
No.
No.
About error of time.
Prigozhin?
Similar?
Prigozhin, the
Because-
Nobel laureate
it's-
Prigozhin?
sorry,
Yes,
his name is Russian name because I say as Russian. Prigozhin. It's Ilya Prigozhin is Russian name, but maybe you know as Prigozhin.
Prigozhin is how I.
Yeah, Bergmann did a lot of non-equilibrium thermodynamics. But I don't know of all of his work. I corresponded with him a little. Did he discuss an arrow of time?
Yeah.
Well, he probably same origin. Yes.
Very close to your
Right.
I think so.
Yeah. Thank you.
Excellent.